Jean-Paul Smets, I'm the CEO of Nexedi. I'm going to give a talk on Wendelin. Actually, the idea of Wendelin started in this room a bit more than 1 year ago, when we discovered that a lot of French taxpayers' money was going to be spent to rebuild what actually this school and INRIA has already built, which is called Scikit-Learn. So we thought maybe instead of spending taxpayers' money to rebuild what already exists, it would be better to use taxpayers' money to help what already exists become better, Scikit-Learn. So we wrote a couple of projects, like you know, European projects, national projects. There are huge amounts of money that governments hardly spend, because subsidies are forbidden in Europe except for research. Then we've got actually a lot of grants and surprisingly many customers. So that's how the Wendelin platform was born. So the leader today of the Wendelin project is Ivan Tiagov, who is there in blue. And not presenting now, there is Kirill Smelkov, who is in the other room. You can probably watch his talk later about out-of-core NumPy. And Sébastien Robin, who did the first prototype, is not there today because he's spending some good time with his family. So the talk will have 4 parts: where we come from, what's the Wendelin architecture. We'll provide one detailed example and give you some ideas about the future roadmap of Wendelin. So where do we come from? Recently we found that actually Nexedi is possibly the largest open source software publisher in Europe if we count how many software we've done or how many lines of code. Probably pretty unknown. We don't have time to review them all, but the portfolio is nearly as large as Red Hat. We are present in France, Germany, Japan, China, and we have all kinds of customers in all kinds of countries, including Airbus, Mitsubishi, Kirin in Japan, and even now Chinese government. Our main way to make money is the logo on the left, ERP5. It's an open source ERP which I wrote 15 years ago, and that can easily compete in many markets with SAP or Oracle. And one day we discovered Scikit-Learn and thought, how can we integrate in a good manner the ERP side of business, which works on the records entered by humans, with the data side of business that works on data produced by machines. That's the first case. Imagine wind turbines. Wind turbines produce logs, but humans who go to the wind turbine to install or update the engine produce records. If we compare the logs and the records, we can predict failures. Then we can plan maintenance. If maintenance has been planned in advance, we can reduce downtime and increase profit for the energy company by 1, 2, 5%, which is actually huge. So we see, collect the records, that's ERP5, predict the failure, that's Scikit-Learn, then plan the maintenance based on the prediction, that's again ERP5. This is a good case of application convergence where the big data and the traditional management merge in the same system. The same way can be done for cars. We can collect logs directly from the engine with this little device called an OBD CAN bus adapter. Those adapters send directly data by GSM, GPRS or 4G to a central storage where we collect all logs from many cars. And if you combine those logs with the records that come from the customer relationship management of the car company, you can predict engine failure or car failure and tell your customer, well, you should go to repair your car next to your place, possibly predict inventory and ship parts in advance, and overall reduce downtime, which will increase customer loyalty and make customer feel he wants to purchase a car again from the same company. Same convergence between the records and the logs, between prediction based on the supervised learning through records of the signal coming from the logs and decision to plan action to keep customer loyalty. Third example, solar energy. That's an example in China, where logs are collected from solar panels that are spread on the fields. Records are stored in the management application, just to know, for example, when the panel was installed, when the farmer has cleaned the panel. Then by watching the logs, we can sometimes predict that one of the panel out of a set of 16 is creating a degradation to the electricity production, because usually panels are grouped in sets of, for example, 16, and then we can plan maintenance to go to repair a panel or just cleaning up from the dust it has. Sometimes it's just a tree that has grown on top of the panel that prevents producing electricity. Again, we add some percent to profits. So these are somehow the cases we are trying to handle through the combination of machine learning and business applications. Let's review now how we've built the Wendelin architecture. First of all, we want to do something that is based solely on completely off-the-shelf hardware. So we just purchase standard servers with SSDs, maybe some GPU, unmanaged switches, no routers, nothing complex, no crossbars, just pure standard hardware, and cables. So for example, with 160 servers, 32 switches and 320 cables, we can create a 5-dimensional hypercube where all servers are connected at least to 2 other servers. That's a very cheap way and very efficient way to make a data center. And I didn't mention it, but the technology that finds the best route from one server to another is called Babel, and it comes from Paris 7 professor Julius Trobocek. It removes totally any management of the cluster. Then, sorry, too fast. So of course, we take the best, say scikit-learn. We already understand that from all the talks we've seen that it's a good choice, and because it's boring, it's easy. And we've been developing for 7 years a distributed database for Python objects that can store Python objects on, let's say, a cluster of independent storage with an architecture that has absolutely no single point of failure or no single point of bottleneck. It's called Neo. You can find information on neopod.org. You will see in a talk that Kirill will provide at 4:45 how we get a kind of magic out-of-core feature for NumPy arrays. So if you allocate what we call a Z-big array, it's just a NumPy array that has an interface to the Neo database, then that array will be transparently cut into pieces and stored in all the little storages of the Neo database. There's no code to change, nothing to do. It provides an out-of-core feature in a distributed shared manner to NumPy with no effort. So go to his talk if you want to know how it works. Then, we've been doing parallel programming for 10 years, where we use a technology that derives from something called ActTalk. ActTalk is a kind of generalization of active object programming made by Jean-Pierre Briot. He's a professor at Paris 6 University, and he does what MapReduce does, but also many other things that MapReduce doesn't do. So we use that. We already got that technology for 10 years in the platform as a service we use. The multi-cloud deployment is done by a tool called SlapOS that has been already used for 5 years in various industries, and we get the full architecture with the cloud deployment, the elasticity, the distributed storage, and on the top, what matters in data analytics, which is scikit-learn. All this is in Python, completely open source. Because we chose Python and NumPy, we get for free the whole PyData and Python data science, OpenCV for video and LTK, Blaze maybe, we'll probably not use it, but Numba and Parakeet or Pandas are definitely very interesting features we can add to the Wendelin system. And that part is less known. It's how do we collect data? Because very often data has been collected, people talk about their Python programming on the data, but they never tell you how do they collect the data. We found a library called Fluentd, made by a company called Treasure Data. They are probably the pioneers in big data as a service. I think they started more than 5 years ago to provide big data as a cloud-based service. Initially, they come from Tsukuba University, where they were doing physics, and they developed MessagePack. It's a kind of protocol buffers, but more flexible and much faster. Then Fluentd has been developed on top of MessagePack to collect logs. That's what Amazon is using to collect all logs in their servers. It has tons of plugins. It's scalable, resilient to network downtime, and it saves bandwidth by compacting messages which are exchanged. So rather than reinvent that part, we thought, let's be compatible with Treasure Data. Let's use Fluentd. Then we are helping to build a standard in data collection. The user interface, we prefer to have it fully in JavaScript and fully rendered on the client side. So we use an abstraction called JIO to access data independently of the backend. It's a kind of virtual file system or virtual database in JavaScript. So the browser does the rendering, visualization, and it can even work offline. So we can keep on visualizing what's in Wendelin when we have bad network. And the server does the heavy-duty data science, mainly in Python. All this with this horrible word, HTTPS, REST protocol. That's actually a good way of making REST protocols. We get a system that has natively out-of-core NumPy, natively parallel, that can leverage bare metal performance. We don't use virtualization. We have transactions. That's very important for business. Without transactions, we can't guarantee a consistency of data, including for ingestion of data. Some SQL queries, and all this at a cost that is about 10 times than anything else you could imagine in the big names of big data. Recently, we won a tender in France, and our cost was just 10 times less than whichever famous name you can think of. Let's see now a detailed example. All this architecture is nice, but does it really work in practice? So in the last 6 months, we tried it on a real case, which is data from wind turbines. First, can we trust Fluentd to collect data? So we set up a Fluentd server on one side, right? And on the left, a Fluentd client close to wind turbines. The server was actually a laptop. We were opening it, closing it, open, close, all the time, so that we have a server with a lot of downtime. We have used the worst network one can imagine, free 3G, with France Telecom roaming. That guarantees completely unpredictability of availability. And for the DSL links, we put ourselves in the deep French countryside with a distance of 10, I don't know, maybe 5 or 10 kilometers to the central office, and that provides really poor bandwidth that sometimes disconnects. Then we checked how much data will be able to flow from the wind turbine to the server. Fantastic. In 3 months, less than 0.001% was lost. We did nothing, we just used FluentD because it has everything in terms of buffer management and ability to try to send again whichever packet has been lost. And for the 0.001%, actually we asked Kirill Smelkov to have a look, and he found a bug in FluentD, fixed it. Actually it should be 0. So great, FluentD, okay. Can we do HTML5 based user interfaces? Which not like Matplotlib, but really everything on the browser side. So we developed some components with an HTML5 component framework called render.js, and we encapsulated some plotting libraries that can navigate in quite large data, like couples of gigabytes. And we checked we could zoom, unzoom, look at a small window, no problem. So fine, we can have everything in terms of visualization done in JavaScript. We can develop more components. One of them on the top, on the bottom right shows an airport in another European country where we have sensors measuring sound. So we could see that it was easy to add more and more visualization components as independent JavaScript components. And could we have a responsive UI? Then no problem. Okay, we can use tablets, desktop, mobile, all good. And the last thing we tried was, can we teach how to use all this user interface to people who don't want to learn Neo, don't want to learn ERP5, don't want to learn scikit-learn, basically don't want to learn anything but JavaScript. So we wrote a small application, I'll provide you the source code after, that stores the data in IndexedDB. So you can see here, we create a JIO virtual database. Instead of storing here in Wendelin, we store locally in the browser in IndexedDB. And we check that the same source code that can have the data handled on the Wendelin platform could work exactly the same if the data was stored locally in the browser. Then it works, it's pretty easy. This way we can split completely in a development team those who do the visualization and front end in JavaScript and those who do the heavy-duty data sciences through this data access abstraction. That brings the next question. Python was super cool 15 years ago, but for kids, JavaScript is even more cool. So, when is the next library done in JavaScript for data science? There are already some things coming out. After all, why are we doing Python if we can do so many good things in JavaScript on the browser side? So we played a game. Let's try to do the whole processing of data completely in JavaScript. How far can we go? Because that's what our customer is asking us. Why should I learn Python? Why should I learn NumPy and scikit-learn? I can do so many things in JavaScript. Here is the answer. For small data set, no problem in JavaScript. We can even launch data processing on server side, for example, by using Phantom.js as a command line launched by popen or whichever popen-like library in Python. Things get bad only once the data is larger than 1 gigabyte. So that gives a good limit. Less than 1 gigabyte, everything can be done reasonably in JavaScript. So this means like an FFT on a 1 gigabyte file in JavaScript might take 1 or 2 minutes. For some people, that's acceptable in terms of batch processing. But after 1 gigabyte, we see various phenomena on the browser of memory leaks or exaggerated slowness. So we just have this rule. More than 1 gigabyte, use NumPy. Less than 1 gigabyte, if you really wish, consider JavaScript. Then we tried something else. do we have any out-of-core data structure in JavaScript? Not really. Everything has to be done by hand, by writing buffers, by loading bits of JavaScript little by little. It requires lots of lines of code. Can we compile Python to JavaScript with mscriptn, for example? What will be the performance? So I tell you, it's absolutely disastrous and unstable. Don't try. You can't do data science in Python compiled to JavaScript by mscriptn currently. However, PyData programs compiled to NaCl or PNaCl, which is actually, it's a fantastic sandboxing technology that is found in Chrome. Probably that could work. So this means that if we have a JavaScript team on one hand doing the front ends, and a true data scientist team on the other hand working in Python, and if we really have to bring some Python good code to the front end guys, and we don't have time to write things in JavaScript or do anything, let's say we really have no budget or time, then maybe we can consider using NaCl or PNaCl to run NumPy code in the browser. This is also very useful for education. Providing NumPy as NaCl to browsers is a great way to create interactive books with high performance. Next, can we store large files not in a file system but in a distributed database? So if we use the proper structure with B-trees of B-trees and putting buckets of the right size, yes, it works. We can access quite quickly any part in the stream and the overhead will be only 0.2%. Okay, we can use a distributed database to store big files. Next, can we use the core model of ERP5 as the model for the monitoring platform? Because that sounds very weird. Why use an ERP to make an industrial platform? So actually in Nexedi, we are kind of a religious sect. 15 years ago, we defined a model that says that any management problem can be reduced to 5 elementary classes. So biologists, they say, I think the same thing for 4 elementary acids. So in our case, it's for 5 elementary classes. And for the last 15 years, we have proven that accounting, human resource management, cloud computing, whichever problem of management can be reduced to the 5 classes. So what about industrial monitoring? So you can imagine management professors don't like it because it means all the faculties of management are actually teaching the same thing. So yes, movement is ingestion of data, resource is type of data, node is data source, pass is data source registration, when we have to say that this sensor can produce that type of data, and item defines the sensor, the data itself, the license of the data set. We come up with this kind of model. It's actually just a translation to the problem of industrial monitoring of the core ERP model of ERP5. And what it means is that we get for free the accounting, the billing, the payment, the user registration, the rule-based security, customer relationship management, and web content management. In short, for any person who has to do a big data project that will become a kind of big data as a service with customers registered into it, pushing data and having batch analysis, by doing this, we save more than 12 months of work and more than 200,000 euro of cost compared to any solution. So now that we have proven that everything in the design can work through a prototype, what is the roadmap? Most of our investment will be in accelerating the learning curve by providing better packages, standard examples, by providing an IPython notebook backend that can connect to Wendelin so that any person who knows IPython notebook will be able to leverage all the features of Wendelin without having to go through learning Fluentd, Neo, etc. Yet, even if this is not, even though such packaging is not yet ready, what you can already use is first the out-of-core component of Wendelin that will be published today, maybe in 1 hour. So during the talk of Kirill, you'll be able to see how it works. Then you can use that Wendelin core for any project that requires out-of-core NumPy. The JIO library, render.js, and user interface sample are also published. You can start, if you like, writing visualization tools that visualize data by accessing the data through an abstract library. All this is available. There are some examples. And of course, all this is open source. In this project, actually, we have many partners. One project has been filed at the French National Fund for Digital Transformation, something like that. And this school has been granted funds. INRIA and Scikit-learn team have been granted funds. Mathematicians at INRIA and École Normale Supérieure also, and Paris 13 University too. They will improve Scikit-learn in a way that's useful to industrial monitoring, but that's also useful to everybody. A company called Second Quadrant has received a grant so that Wendelin will be able to use Postgres as a backend in addition to MariaDB. Abeliant will produce visualization components that can be used in Wendelin and outside Wendelin. Nexedi, we are doing mainly the platform and database. And there's another project financed by the Eurostar framework where MariaDB will also receive funds to improve certain parts of the core of MariaDB. Overall, we've been able to manage that 100% of the funds end up improving widely used open source projects. We have the help of industrials. So one is the Russian subsidiary of Mitsubishi in Russia. There's also the Y Corporation and the X Corporation that have not yet granted us the right to provide their name, but I think this will change in the next 3 months. So this ends the talk. Thank you.